Hey, welcome back. In this video we are going to talk about preparation and reaction of alkyl halides. So without any further ado, let's dive into it. Okay, let's start first with preparation or synthesis from alkanes of alkyl halides. It is a radical involved reaction and goes through three steps: initial step, propagation step, repeating cycle, and termination step. But I will not go to that mechanism in detail. You can find that in internet or elsewhere. What is in our interest is the straight reaction with light, and is going to give in a ratio 30 to 70%. Why? Because primary are less stable than secondary and secondary are less stable than tertiary, or in other words, the stability increase on this side from primary, secondary and tertiary. Hydrogens. This is related with a dissociation energy because tertiary hydrogen has a lower dissociation energy compared to the secondary hydrogen that is even higher, and primary is even more higher than secondary. So that's why you have more formation, and also this impact also the radical stability. Stability of a tertiary radical is higher compared to the primary or secondary radical. Okay, this is not so much used as a reaction because it gives a lot of product, okay, but just for completeness. Let's move now to the second method that we can synthesize, or in other words, prepare alkyl halides. This is from alkenes. We learned from our previous videos that from a double bond alkene, if we react that with an HX, X represent chlorine, bromine, iodine, the halogens, you can yield a Markovnikov product. Okay, or if you do halogenation, you're going to halogenate the double bond. Okay, this should be known by you by now. Another way to synthesize alkyl halides from alkenes is by using NBS or N-Bromo succinimide. This compound here break this bond here by removing this hydrogen that is in allylic position. Allylic position is one carbon away from the double bond. This hydrogen here is called vinylic position. Okay, this is allylic position. This is the NBS and gives an allylic halide. Okay, this is another way. It is measured experimentally that vinylic position has less stability than primary, than secondary and tertiary radicals. Allylic radical is even more stable. But why? The simplest answer for this is the resonance. Because allylic position has the option to do resonance because this double bond can move here and this can move here, this electron. So, and you should know that resonance stabilizes the molecule. More resonance structures, more stabilized is the molecule. Who is the real one is something in the middle of these two. Okay, here this compound gives a single product, but if we try with NBS here, due to the resonance structures, it gives the possibility to give more than one product. So from this structure here, if we do, it is going to give first in the allylic position, okay? But this double bond can move here and you can have another compound, okay, due to the resonance structure. So be careful. If the compound is symmetrical, like in this case, here, there is no other compound, there is no other product, only one. But if the compound is not symmetrical, it has different positions, is going to give more than one product. Let's see this one, for example, to further conceptualize the process. So here, if we treat this compound here with methyl cyclohexane with NBS, you're going to have 1, 2, 3, 4, 5 compounds. First substitution is going to be here. Second substitution is going to be here. Third substitution is going to be here. Fourth substitution is going to be here. Here. Fifth substitution is going to be here. Okay? So you have 5 compounds. You have to be careful when you use an MBS. If you do not have a symmetrical compound, it's not going to give you a single product as you may desire. Another way to synthesize the alkyl halides is from alkyls. Starting from methyl alcohol to primary alcohol, secondary alcohols, and tertiary alcohols, reactivity increase. Tertiary alcohols are easily prepared by using directly the hydrogen bromide or hydrogen chloride or hydrogen iodide in ether and gives the halogen. But with primary and secondary alcohols, the reaction is so slow. So instead of that, we are going to use thionyl chloride and phosphorus tribromide. These are the two most common reagents that are used to convert primary and secondary alcohols to alkyl halides. So this one is going to give. Okay, so can you give a name for this one? 1, 2, 3 carbons is 1-chloropropane. And this one here is going to give the brominated one. Depends on your need. Again, with secondary alcohols, or if we treat with HF and pyridine, you're going to have fluorinated. Let's move now to the reaction of alkyl halides. The first one important to mention is Grignard reagent. An alkyl halide can react with magnesium in ether solvent to give this compound. This is so sensitive to the protonation. So because magnesium has a delta positive and the carbon takes a delta negative due to the difference in the electronegativity, carbon is more electronegative than magnesium. And if you have that in a hydrated place, it's going to be protonated and to give the alkane. Okay? If you need that, you can do this step. If no, be careful. Keep it only in the ether solvent. Okay, primary, secondary, tertiary alkenyls, I mean the halogen replaced to the vinylic carbon, to the double bond, and allylic halogens can react with magnesium. Okay, keep this in mind. This is called Grignard reagent. So from the alkyl halide we can yield, if we want, an alkane. The second common reaction for the alkyl halide is diorganocopper compounds, or Gilman reagents. If we treat an alkyl halide with lithium, it's going to give a lithium alkane. And if we treat this lithium alkane with copper iodide in ether, it's going to give this reagent here that is called Gilman reagent. It contains 2 because copper has 2 valent. Is 2-valent, and with lithium as a salt. This serves as a salt. So this reagent gives the option, if this react with an alkyl halide, to do alkylation, to add more carbon to the chain. So if we go further with this example, it's going to connect these 2 carbons, 1, 2. Okay? This is the product that you get. But it's important because you have addition of 2 carbons. You can add even more, 3, 4, 5. It does not work with fluorine, it works with vinylic, it works with allylic. Okay? Okay, let's summarize now with another example. That is a multi-step synthesis. So what is going to be the first reagent? In order to convert the double bond to an alcohol, because here has happened a change. So because you can see this is a secondary alcohol, not is the substitution has happened here to give a secondary alcohol, not here. If it has happened here, it should have been a tertiary alcohol. So the hydration has happened on the less substituted carbon. This reminds us what? Hydroboration oxidation reaction to give a non-Markovnikov product. Okay, now you have a secondary alcohol here, and you want to convert that to an alkyl halide. So what we learned above, in order to convert the secondary alcohol to an alkyl halide, you cannot use directly HBr, like you should come in your mind in this case, but a special product that was phosphorus 3-bromide in ether. Okay? It works with primary and secondary alcohols. With tertiary one, the story is different. You can do directly with HBr, but this is secondary alcohol. And now you want to remove this bromo here and add a metal. How you could do that? As we learned, we can use diorganocopper compound. So if it's only one metal added or one carbon, use just one with copper and lithium in ether. How was this compound called? This reagent called Gilman reagent, and gives this compound that is alkylated with one metal. Okay? Keep this in mind. Thank you so much for watching, and see you in the next video. Peace.